As galaxies are the building blocks of the universe, so stars are the molecules in those blocks. But what are stars and how do they form? Our nearest example is the Sun, a gaseous inferno, a cosmic compromise between nuclear forces blowing outwards and gravitational forces pulling inwards, a balancing act that will eventually wobble. $15 billion years ago, in the maelstrom of gas and dust that followed the Big Bang, the first stars took shape. They preceded the first galaxies, for without stars, there can't be galaxies. These early stars began to group together. Some may have survived to this day. Globular clusters, as they're called, are to be found orbiting over the center of galaxies, galaxies which formed long after the clusters. Galaxies were born 1 billion years after the Big Bang. This one has 1 million stars. And this one has 1 million stars. A galaxy grown fat by gobbling up others. The process can be seen today. Here, 2 galaxies in the act of a heavenly merger. A more modest galaxy, the irregular form of the Large Magellanic Cloud. And a spiral galaxy, shaped like the letter Z. With 200,000 million stars in its sphere, this spiral is more tightly wound. It's a typical medium-sized galaxy, not unlike our own, the Milky Way. In simulation, this is an edge-on view of the Milky Way. The globular clusters, a yellow halo around the center. Their ancient stars are between 12 and 15 billion years old. Our own star, the Sun, is much younger. It formed 4.5 billion years ago and lies in a spiral arm towards the edge of the galaxy. It's nearby that stars are conceived in a vast bubble of hydrogen. We can see it from Earth in a neighboring arm of the spiral within the constellation of Orion. Inside this cloud of dust and gas, matter is squeezing ever denser. Gravity increases, temperatures soar, nuclear fusion begins, and stars are born. This is a photograph of that stellar nursery, M42, the great nebula in Orion. In the 90s, the region came under the powerful scrutiny of the Hubble Space Telescope. For the first time, we could glimpse hot new stars surrounded by great disks of material. In the case of our Sun, it was such a disk that evolved into the planets. The Milky Way is full of places where stars are born. It was in a dark area like this, a Bock globule, where the Sun first shone. Jolted possibly by a nearby explosion, a cloud condensed to become our star. Settled now into comfortable middle age, the Sun shines yellow with a surface temperature of 6,000 degrees Celsius. And that's how it'll be for the next 5 billion years. A nuclear reactor steadily converting hydrogen into helium. But when the hydrogen runs low, our star will begin to die. Desperately, the Sun will start to fuse helium. It'll change color, and it'll grow. Mercury, Venus, and Earth will be consumed. The Sun will be a red giant, its nuclear reactor out of control, an unsustainable situation. Finally, its fuel spent, the sun will slowly collapse. Then, over a prolonged period, material will be puffed into space. The sun itself will be a corpse, a white dwarf no bigger than Earth, so dense that a sugar cube of its matter would weigh a ton. Such a relic can be seen in the constellation of Aquarius. It's called the Helix, a nebula wafted out by a dying star. But here are the remnants of a more spectacular death, the nebula of a gigantic star blown apart by a cataclysmic explosion. Astronomers call it a supernova. The materials in these vast nebulae have played a vital role in our galaxy, for it's only the biggest stars with over 8 times the mass of the Sun that go out with a bang. Were it not for supernovae, we'd have no heavy elements, no iron or precious metals, or the phosphorus and sulfur vital to living cells. In our own galaxy, many giants are destined to go supernova. One of them is Rigel in Orion, 50,000 times brighter than the Sun. And in the same constellation, the great star Betelgeuse. It'll go within the next 10,000 years. Superstars are formed from superclouds. The process is like the birth of the Sun, just bigger. A massive nebula of gas and dust condenses. As it falls in on itself, gravity increases, temperatures soar, and a nuclear furnace fires up. Because it's so big, perhaps 100 times the mass of the Sun, the superstar burns fierce and bright. Enormous gravity at the center creates prodigious heat. As a result, the star can fuse a gamut of fuels at an incredible rate. But its life will be short, maybe just 10 million years. In middle age, the superstar spreads. It gets cooler and redder. At the center, helium is converting into the heavier elements. When iron is formed, energy is no longer being created, but absorbed. The red giant collapses. The resulting explosion is a supernova. As material is shed into space, and providing the giant had been big enough, a remnant remains. It's a neutron star, rotating once every second. Just 30 kilometers wide, a pinhead of its material would weigh 1 million tons. There's a neutron star in the Crab Nebula. It can be seen optically, its twin magnetic beams pulsing like a lighthouse. A red giant in cross-section reveals the anatomy of a catastrophe. As it ages, the giant fuses more and more elements, not just hydrogen and helium like the Sun, but heavy metals. They form internal shells. An iron core is created only to collapse and explode. It's supernovae that have seeded the universe. They've distributed the heavier elements and provided the basis for life. If the surviving core of a supernova is more than 3.5 times the mass of the Sun, then it'll collapse beyond the stage of a neutron star. It'll become a black hole.